Okay, so good afternoon, everyone. Welcome to the afternoon session of this room. And there will be two speakers in total, and they are representing ODs of the frontier science world of the category of functional analysis and operator theory. The first speaker is Professor Hanfeng Li from State University of New York at Buffalo, and the title of his talk is L2 invariants and dynamical invariants. Yeah, that's what let's enjoy.
Thank you. Um, I really would like to thank the organizers very much for such a wonderful conference. I will talk about the relation between L2 invariance and dynamical invariance. This is mainly based on the joint work with Andreas Tom, though I will also mention a bit work with Bingbing Liang. So first of all, what are these two things, L2 invariance and dynamical invariance? Well, in L2 invariance, the simplest is basically just the topological invariance, but using operator algebra tools. So how does it work? The simplest case is that you start with a say finite CW complex. Then usually you can look at the homology, cohomology. You can look at the Betti numbers, for example. Okay. But then another way to handle these things is that you lift them up to finite covering space. Then you look at the homology, cohomology there, and Betti numbers there. Then you try to normalize it, divided by the number, how many covering there. Then get back to invariance to the original space. But then you can actually go to infinity, as we typically do in mathematics. Actually, you go to, for example, just the universal covering space. Then you get homology there, but because typically the fundamental group is infinite dimensional, then the homology cohomology of the universal covering space is not finite dimensional anymore. Okay, you don't get a finite number. So if you still want, for example, Betti number, then it's infinite there. Okay. However, the fundamental group of the original space acts very largely on the universal covering space. So it acts on the homology cohomology. So though the homology cohomology there, they are infinite dimensional, but you have the group acting on it. If you module out the group action, it turns out to be actually finite dimensional. So the idea here is that to look at the invariance, homology invariance for universal covering space, you try to module out the action of the fundamental group. To make it precise, how to really do this modulation, then you really have to use operator algebra tools, which means from algebras or system algebras. The other side for the dynamical invariance, well, the dynamical systems have very different settings here. We'll just concentrate on the topological dynamical situation. So some of these results actually can also be put in the framework of measurable dynamic system, measurable preserving actions. But here I will concentrate on topological dynamics. So we look at actions of continuous actions of countable discrete groups on compact metrizable spaces. Okay. Then depends on the situation, what kind of invariance we want to look at. We will actually specify the group. Yeah, sometimes required to be minimal, sometimes required to be even more specific, for example. Yeah. So in short, one can say that what we want to look at here is L2 invariance, and they are based on open algebras, and the dynamical invariance on the other side. Of course, on each side there are many invariants and properties. So the ones we are looking at here is on one side, on L2 invariance side, we are going to look at the L2 torsion, which is based on Fourier-Cartesian determinant in operator algebras. Okay. On the dynamical side, we will see that we have topological entropy there, and they correspond to each other. This will be actually in the joint work with Andreas Tom. Another correspondence here is that here on the arbitrary invariance side, we have the fundamental rank, or you just say one of the arbitrary Betti numbers. On the other side, on topological dynamical side, we have the mid-dimension. They correspond to each other. Of course, these invariants are defined in totally different settings. When I say they correspond to each other, I have to specify a common setting so that we can make sense of both of them. Then we can say they are actually equal, for example. Yeah. So let me start with the condition of the group here. So for most of this talk, we'll mainly just consider minimal group. So a discrete, countable discrete group minimal is a minimal just means that you have almost the invariant find sets. So that means we can find a sequence of non-amplified subsets of the group so that they are almost the whole thing in the sense that when you do multiplication, they basically don't change. Okay. So this is just taking an element in the group, you multiply it on the final set. You ask whether it's really the same as the original set. Then you do the symmetric difference there. This is finite, so you look at the cardinality. You hope that it's very small, but it's finite set. The cardinality, if it's not 0, then it has to be at least 1. So what we really do is compare it to the size of the original set and require that this becomes very small. So you let n go to infinity, then you require this to be 0. The simplest example of minimal groups would be just typically one is just the integer group or finite groups, but mainly in dynamics we frequently will look at the integer group. Also this D and more generally or minimal group or abelian groups, Newtonian groups, solvable groups. Now we're going to talk about the right-hand side of the first correspondence, the topological entropy. So we consider one action of a countable minimal group on a compact metrizable space. To define the entropy, we look at finite open covers of the space. We look at the minimum number of elements of the open cover to cover the whole X, because sometimes you can solve with some of those open sets. You are still able to cover the whole X. We also look at the join of open covers. So if you have two open covers, you can take one open set from each guy, take the intersection of them, put them together. That's a new open cover. But it defines the original ones. Everything becomes smaller. Then the topological entropy introduced by Adler, Hanfeng, and Michelangelo, following Kolmogorov-Sinai's measure entropy several years before. Then is the following: you take, you find open cover. You look at this Fn, this for sequence. This is this comes up in the definition of a minimal group. For each element in this set, you pull back your open cover, you still get one open cover. You take the join of all these guys. Then you look at the minimum number of elements you need to cover the whole space. This, of course, this typically will become larger and larger as n becomes larger, because this final set becomes really large. Then we look at how fast it grows. It turns out that frequently this actually grows exponentially, so we take a logarithm divided by the size of the final set. Then it's a non-trivial, but there are theorems there. Basically, the Warren-Weiss lemma guaranteeing that the limit always exists. So, and this limit is always non-negative and finite. But so you get one number here, and this number depends on the finite open cover. Then we take the supreme of all such finite open covers, or you simply just require the diameter of the take a sequence of open covers requiring that the diameters of each open set in the open cover becomes smaller and smaller going to 0. then you can take the limit. Yeah. Then this is the definition of the topological entropy of the whole action. Yeah. Now you get a non-negative number, and possibly you get infinity. This is the definition, but what it describes is that is the complexity of the action. Just some simple example: if you take rotation on the unit circle, you fix any angle to the rotation there, that's one homomorphism. But then it generates one action of the interior group. Yeah, this one is fairly simple because actually it preserves the metric. So the entropy actually will be actually 0. On the other hand, take for any minimal group, you could for any finite set A, you can look at the shift action of gamma on A to the gamma. You take this is just you take a copy of A for each element of your group, take the product of them, and the group acts on itself by you can use either left multiplication or right multiplication. Then automatically it induces one action on the product space, this so-called Bernoulli shift. And for this one calculates that the entropy is always just the logarithm of the size of A. A is any finite set, finite non-empty set. Take any one. So that's entropy. Next, we're going to talk about the left-hand side. For the first correspondence, that's the Fourier-Casson determinant. For this, we have to talk about the group ring. So now we have for the still the countable discrete group, but here you don't need to assume it to be minimal anymore. It could be any group. Then the integral group ring is basically just turn the group into actually one ring, basically. You do all the integer coefficients and you make it into a ring very naturally. So formally you can think of elements there as finitely supported functions on gamma with values in the integer. And you write each such function as a power series. So f sub s is just the value at s, and s is the group element. So this is the value times the group element, you map and add them together. But here, in fact, everything is finitely supported, so it looks like a power series. It's actually just a finite sum there. Yeah. Then for multiplication, for addition, then you just do the addition pointwisely. For each group element, add the coefficients together. For multiplication, then you just use the distribution law. So you just need to worry about how you multiply f sub s times s and g sub t times t. But f sub s and g sub t, they are just integers. So of course we know how to multiply them. For s and t, they are in the group. So we also know how to multiply them. Okay. So this is the definition of the group ring. Yeah, integral group ring. If you want, here we say integral because the value coefficients here are all integers, but you could replace it by other things like complex numbers, for example, or zero numbers. Some of these group rings are actually very simple, very easy to describe, and very nice. If you, for example, for the case the group is just integral group itself, then this integral group is simply just the Laurent polynomials with integer coefficients. So the one here in the group just corresponds to the polynomial variable x. And the next one here, then it just becomes x inverse. If you have z to the d, gamma is z to the d, then the integral group turns out to be similar, still Laurent polynomials, but now you have d many variables. One specific situation related to arbitrary invariance is the following. You take a connected CW complex, so that you can think of it to just say finite. Then you look at the universal covering space. Then the CW complex structure naturally lifts up to the universal covering space. And you look at the relative homology groups there. Then this becomes very naturally if we left the gamma module, where gamma is just a fundamental group of the original space X. So the gamma acts on X on the universal covering space, and the quotient space is just X itself. Then gamma acts on the relative homology also very naturally, and we're seeing that this is actually a free left module where the basis just corresponds to the n cells of the original space. So, I mean, here, this is, you see, why the group periods come up when we find the CW complex and go to reverse covering space where they should appear. Okay. Now we can talk about the Fourier Casson determinant. So we take one element in the integral group period. Then here, we earlier mentioned that this is a reading, so you have addition and multiplication, but in fact, you also have a so-called star operation. The star operation is very simple. You basically just take star of f sub s and s for each of them. But the f sub s is just the integer, so the star is just simply itself. If you treat it as a complex number, think of a complex conjugation there, because it's integer, this is just itself. For the group element, the star is simply just the inverse. Okay, so this is the formula for f star. We'll also need some norms here. Very simple norm to put is just one norm, just add take the absolute value of the coefficients, put them together. Then there is one very canonical trace for this group period. You simply take the coefficient at the identity element. So trace, why is it called a trace? Trace simply just means that in general, when we look at those examples, when gamma is z and z to the d, the group periods are very, very nice. But once the group itself is not abelian, the group ring is not commutative. Okay, so in general, this group ring is not commutative. The trace simply just means that it's linear, and the trace of f times g is equal to the trace of g times f. So that's what trace means. Just like the trace of matrices, square matrices. Just like, okay. Yeah. So it kills the trace somehow kills the non-commutativity. Then for whenever this f is actually self-adjoint, but don't want to talk about that, so I will just say we look at f star times f. Okay, yeah. Then for f star times f, there is one Boyer probability measure on the real line. It turns out that this measure is actually supported on the positive half. Actually, more than that is actually on some bounded interval there. Yeah. So here we write down the one bound for the interval here, but there one norm, but actually that doesn't matter. The main thing is that this is just the one bounded interval. Okay. And on the positive half side of the real line. Yeah. It's determined by this property. So you take in the end, look at the monomial t to the n, take the integral of it under this measure. Then this should be equal to just for f star times f, you take the nth power, take the trace. This is so-called spectral measure. So the existence of such measure is actually unique. It's a standard using system algebra techniques. Then the Fourier Casson determinant, they introduced it in 1955, so more than 70 years ago, is that you look at this measure for f star f, look at spectral measure there, you take the logarithm of it. Okay. Then you take the logarithm, your logarithm function, you take the integral on this measure. Then because here I'm putting f star f, I have to normalize it back to actually divide it by 2. So then we take the exponential. Then it turns out that this is just this number is always finite and non-negative. Though here for simplicity we're defining it only just for elements defining the Fourier-Casson determined only on the integral group ring, but actually the most appropriate setting to define such things is actually on a Hanfeng Li algebra, with or just say Hanfeng Li algebra with a trace, normal trace, or just say generally you can do it for a unit of system algebra with a trace state. Now here are a few examples of the Fourier-Casson determinant. When the group is, so in the case the gamma is, the group is simply the D, it turns out that the Fourier-Casson determinant is actually equal to the so-called Mahler measure introduced by Mahler in number theory. So actually Mahler introduced the Mahler measure after Fourier-Casson determinant was introduced. So in this case, when we have an element in the group ring, using Fourier transform, you can think of the element, the group, integral group ring is actually contained in the infinity functions on the d-dimensional torus. If you treat element f as an infinity function in this way, then the determinant is simply just you take an absolute value, you take a logarithm, take an integral for the normalized Haar measure. So here mu is the normalized Haar measure. Then you take the exponential. Yeah. When Mahler introduced it, this is basically he defined it, how the way he defined it. But when the group is integer group itself, in the case d equal to 1, the Mahler measure could be calculated even more explicitly, and this is why it comes up in number theory. Okay, so in this case, the group ring is simply just a Laurent polynomials, so you can multiply it by some power of the variable to make it actually really a polynomial. And this is just assuming that the zero coefficient and the leading coefficient is both non-zero. So you can do this unless f is 0. Okay. Then, in this case, the Fourier-Casson determinant is very explicit using roots and the leading coefficients. It's simply just the absolute value of the leading coefficient. And the times what you take all the roots of it, counted with multiplicity, and you take the absolute value of the roots. If it's smaller than 1, you forget about it. If it's bigger than 1, you take the multiplication. Now we can really state the correspondence between the determinant and the entropy. For this, we have defined both sides, but we need the common setting so that we can compare both sides. The setting is the so-called algebraic actions. So these are the actions of the group on compact metrizable abelian groups where continuous automorphisms of the group. So you can already see here, so there's some algebraic structure involved, but the aim of this kind of actions, called algebraic actions, really comes from the next scene. That is, there's a very natural one-to-one correspondence between countable left modules of the group ring with algebraic actions. Yeah. So the correspondence is simply just the following. The gamma modules is basically the same as gamma acting on a discrete abelian group. Okay, yeah, because we are using integral coefficients. Now, gamma acting on a discrete abelian group using topological duality, the discrete abelian group is the same, contains the same information as its topological dual. This is the topological dual. That is this group of all group homomorphisms from the discrete abelian group to the unit circle. Then this topological dual becomes a compact abelian group. The topological duality simply says that they correspond to each other. They contain all the information, the same amount of information. Yeah. So the gamma action on this countable discrete abelian group is the same as gamma action on the Panzer Q. That is the algebra action. Then in this way, you can actually write down a lot of algebra actions for any group. Just simply write down a modular. In particular, if you want to look at some non-trivial example, not free modules, so you just take one element in the group in, look at the left ideal generated by it, the modular out. And this actually already gives us a very interesting non-trivial algebra action, so-called principal algebra action. Yeah. Then in 2006, Christopher Denninger actually first suggested that in the non-commutative case, when the group is non-abelian, the determinant, Fourier determinant, should be related to the entropy. The precise condition is that you want f to be actually not a zero divisor. This simply just means if f times g equals 0, where g is also an integral group, then g should also be 0. The under this condition, her suggested that the entropy of the corresponding principal algebra action, that is actually this one here, should be basically equal to the Fourier determinant, but not precisely. You have to take a logarithm for the Fourier determinant, because on this side, there is one exponential involved in the definition. Yeah. Prior to Denninger's question, actually, this was done completely by Jusminsky at the very early stage of algorithmic theory for the case gamma is just the integer group. Then Lindensaus, Schmidt, and Watt did this for the D using commutative algebra tools. Yeah. So in these works, they did not mention Fourier determinant because, well, they just used the model measure. Because orbital algebra things actually are not tools for not toys for these people. Yeah. So then Denninger is the first one who noticed that when you go to non-abelian groups, you don't have a modular measure anymore. Then you should actually use a Fourier determinant. Yeah. So he asked this question and proved it under some special conditions, and also Denninger and Schmidt, and me also later for various special cases. Then with Andreas Tom, we showed that this is indeed true in general for all minimal groups. Yeah. And also later, though when Denninger posed the question, at that time, the entropy theory was only known for minimal group, but later the entropy theory has been extended to the larger class of groups, the so-called Sophie groups. Then Ben Hayes showed later that this is actually also true even for Sophie groups. So that is that's a correspondence between determinant and entropy. Now we want to move to the torsion. So, for this, we need to introduce one condition, so-called Wolfgang-Lucas determinant determinant condition, which is implied by the determinant conjecture. So first of all, everything we said about the trace and determinant actually extends to the matrices over the group. And then the determinant conjecture says that if you have elements in the matrix of the integral group and a self-adjoint, then this modified determinant is always at least 1. So what is this modified determinant? It's basically almost the same as the original determinant, except that when we take an integral, we throw away the 0 point. Okay. Yeah, that's the only difference. We are not taking, when we take integral, we don't count the 0 point. The thing here is that maybe the spectral measure has partial mass at the 0 point. In that case, then the original determinant for this integral here, it must be negative infinity. Then the determinant becomes 0. So in this way, you make it larger. But the y, that's going to suggest that this should be at least 1. This just comes from that it has integer coefficients. So basically, when you have an integer matrix, the analog of this is just that we take all the determinant should be basically product of all those roots for the characteristic polynomial. Yeah, but then this modified one should mean that you still actually here it does not depend on the metric. It actually only depends on the topology. The metric gives you more information, and the topological entropy actually does not depend on the choice of the metric. The right-hand side here, the definition uses the topology of X sub f. Yeah. Okay, so this is just an analog of that for the matrix, where you for this modified ones, you are only looking at the product of the non-zero roots of the characteristic polynomial. Okay, then you know that when you have integer matrix, then that should actually what you get should be an integer. So this is why I suggest that it should be at least 1. The article and example showed that this is true for survey groups, in particular for minimal groups, and this condition implies that for an f in the matrix of the group ring, if the kernel is 0, here the kernel means that you think of this Z gamma acting on the L2 gamma, just gamma acts on L2 gamma by left regular representation. Then we have a matrix, it acts on the direct sum of the L2 space. And here you're seeing that as a bounded linear operator, the kernel is 0. Yeah. In this case, then the determinant should be at least 1, because in this case, actually, at the 0 point, the spectral measure is 0. So this is the same as this one. Then here's the definition of vector torsion. This is vector torsion can be defined in various slightly different settings. But this is a combinatorial way to define it, and it's kind of a little bit algebraic. So you look at the left module over the integral group ring. It's required to have type FL. What does this mean? Is that you have a resolution by finite free modules. Okay, so this is a ring here, and you take finite many copies of it. Look at this free module. You require that to have a short exact sequence. Yeah. Then what you do is that you use the gamma acts on L2 gamma, we just mentioned. So Z gamma, so L2 gamma is also a module over the Z gamma. You take a tensor product with L2 gamma. So then you forget about the M. This is typical in homological algebra. Then you get this sequence here. Yeah. Then you require in homological algebra, then what we ask is to look at the homology of this chain complex. And here we're having L2 gamma, so everything actually will be bounded. And I mean, this decay here is actually given by a matrix over Z gamma. They are all bounded linear operators. We go to L2 gamma here. So everything is bounded. So instead, if in homological algebra, you might just want to say, ask whether what's the difference between the curl and the image, right? But here then you have full function analysis there, so you can just everything is bounded. You can ask what's the difference between kernel and the closure of the image. Okay. And here we are assuming that they are always equal. So basically, you can say there is no homology here involved. Everything is still exact. That's why it's called the weakly exact. You can ask what happens if they're not equal. If they're not equal, then you can look at the difference there. Then you get to the L2 Betti number. Okay, so this is L2 torsion is the secondary invariant. Only you care about it only when all the L2 Betti numbers are 0. And we also assume the determinant condition holds. In particular, it holds for amenable groups. We know that. Okay. Then Curry and Matai and Luca and Rosenberg introduced the L2 torsion. So they defined it to be just the determinant of this, basically the Laplacian at each stage. Take a determinant at each level, then you take a logarithm, multiply by j, and take it all to the sum. And it does not depend on the choice of the resolution. Yeah. So it does not depend on the choice of this exactly this sequence here, we choose. And we also know when the sequence is actually short exactly. So when gamma is minimal, Eric showed that this happens exactly when the order characteristic is 0. That is just ordinary the sum of the size of all these free modules. Then with Andrews Tom, we showed that when gamma is minimal, and the left module is of type FL, and the order characteristic is 0. So these two conditions just say that the torsion is defined. Then we can show that the torsion is actually equal to the entropy. As here, I will just mention one application of this theorem. So in the case we always have the trivial module. So basically, you let gamma act on Z itself completely trivially. So you can make you always have this very trivial module for the gamma. If this trivial module has the torsion defined, then the torsion of the group is simply defined as this torsion. Yeah. Then and we also by results of Weinberg, Garnier, and Wall, we know basically we know some sufficient condition for the torsion to be defined. So when when gamma has defined the classifying space, that means find connected CW complex with fundamental group being gamma, and the universal covering space is contractible. Okay. In this case, then the trivial module is of type of FL. So and the gamma is actually finally prevented. Yeah. Then Wolfgang conjectured that if gamma is minimal, non-trivial, and has a finite classifying space, then their torsion is 0. Okay. And then Wegler showed that this is really true if gamma is further assumed to be elementary minimal. I'm not going to discuss the definition of elementary minimal. I will just simply say that this is a smaller class compared to a minimal groups. It's defined inductively. Kind of inductively. You have to use transfinite induction defined. It's the smallest class of groups containing all the finite groups and the abelian groups and the closed undertaking subgroups, quotient groups, inductive limits. So basically, you can use transfinite induction to handle this class of groups. Yeah. As a corollary of our theorem here, one can get that one can show that Lucas conjecture is really true when the group is minimal. Yeah. The point here is that in that kind of a situation, this is just a Z, and then this is just simply just an action on the dual of Z, which is a circle. And the point is that this action is actually trivial. And the condition can easily show that it implies that the group is actually infinite. Now in dynamical system, it's very easy to show that once you really look at the definition of entropy, that if the group is infinite and the action is trivial, then the entropy is always 0. So the question on the right-hand side, pointing out on the right-hand side, is very easy to show that the entropy is 0. So we'll get to that the left-hand side is 0. So that is the correspondence between entropy and torsion and Fourier-Casson determinant. Next, I will talk about the correspondence between mean dimension and the von Neumann-Luck rank. So the mean dimension is another invariant in dynamical system introduced by Gromov in 1909. It's the dynamical analog of covering dimension. So you still have the action there. Then you still take a finite open cover. You look at how many of these open sets actually overlap. Okay, that's the order of the open cover. Then you can refine your open cover, take another open cover, but each one of them each one open set here is containing some open set of U. Okay. Then you look at the order there, take the minimum value. And you get a real number for this open cover U. If you let the diameter of the elements in U go to 0, then take a limit, then this is the definition of the numerical cover dimension. Okay. Then the mean dimension is just the dynamical version of this one. So you look at the Fourier sequence, and for each group element, you put back the open cover, take the join of them. This is the same as before for topological entropy. Now you take this D number. This time it does not go exponentially anymore. Typically it goes linearly. So you divide by the size of F1, take a limit. Again, once and once lemma guarantees that the limit exists. And then again you take the supreme, or you say maximal. I should really say supreme here. Over all the finite open covers. That's the definition of the mean dimension. Now, if you, for example, if you look at still below the shift, but here is the interval, unity interval, or a cube of it, d-dimensional, then the mean dimension becomes just this number d here. The phenomenon rank, well, then for this one to define it, earlier I tried to avoid using the orbital algebras, talking about only the integral group theorem, but here we have to talk about the group theorem. We have to talk about the group of fundamental algebra. So we look at the group of fundamental algebra for gamma. This is just all the bounding linear pairs on L2 gamma, computing with the right circular repetition. Then the trace still extends to it, and the group theorem, integral group theorem can be naturally considered to be part of the group of fundamental algebra. Yeah. Then for finitely unitless trace, for any finitely generated projective module over the fundamental algebra, one can talk about the dimension of it. This is very standard in the K-theory for K-zero group. Yeah. So you write the module as coming from some idempotent, then you take the trace of the idempotent. Yeah. For arbitrary module, this is a contribution of Wolfgang Look, because in K-theory, typically this is what you get. Only for finite generated projective module, but Wolfgang Look extended this to arbitrary module. So what it does is that look at for any module, you take all the finitely generated projective for some modules. Take a dimension there, take the supreme. Okay. Yeah. Then for now, this is for modules over the fundamental algebra, but if for integral group theorem, you simply take the tensor product, make it into the module of the fundamental algebra, then you take the dimension. That's the fundamental local rank. Then with Biminian, we showed that when gamma is minimal, for any module, the fundamental rank is actually equal to the mean dimension. Okay. Then Ben Hayes later showed that for surface groups, but for the module to be satisfying some special modules of finitely generated ones, this is true. Then with Biminian, we also showed that this actually shows for generality for surface groups. There's also one application here for on the dynamical side. Earlier application is on the torsion side. Here I want to give an application on the dynamical side. So for the gamma, you can look at the subgroups of rational numbers generated by 1 over the size of the group for finite subgroups. Then there is one conjecture, the so-called strong archaea conjecture, which is known to be false now, mainly due to Tim Austin. But it's also known to be true for many groups, in particular for elementary minimum groups, for which the finite subgroups of this have the bound on the size of finite subgroups by linear. Then for this, if the group satisfies this condition, then for any module, one consider the mean dimension of the algebra action is always in this subgroup, together possibly infinity. Yeah. The point here is that under this condition, actually, it's very easy to show that the left-hand side is always contained in that set, that the subgroup and the possible infinity. Then you get the right-hand side is also there. Yeah. All right, let's stop here. Thank you very much.
Okay, thank you very much, Professor Li, for the wonderful talk. Any question or comment?
Yes, it's defined for any group. For that, yes, you have to define the entropy for actions of any group. We don't know how to do that. Yes, that's exactly the point. Yeah. Huh? Yes, we do know how to define the left-hand side, define the determinant. So that suggests there should be a definition for topological entropy for actions of any group. There should be.
Any other question?
Sure.
Is there an example that can easily L2 where the torsion was not zero for a group? You had a theorem that the torsion is zero.
Not from this. Oh. If you want, yes, there are examples, but people even calculate like for hyperbolic group or something like that. But if you want to just look at the theorem here, so from this theorem here, you can easily find the examples. I think you can easily find the examples where the right hand side is not zero.
Yeah, I'm not an expert, so the right side I didn't know those examples. Maybe after.
Any other question, comment?
So in identity, Von-Neumann rank.
Yeah.
That slides. Yes, just. Yeah.
So here,
This
yeah.
I see this identity can be the abstraction for a discrete group to be amenable. So I want to ask: have you tried to compute the Von-Neumann rank for Thompson's group?
No. I mean, this should be fundamental rank for the Thomson group. No, because it really depends on the module. You have to say which module you want to use and to calculate it. Yeah. Also, on the other hand, this actually also is true not only for a minimal group, as we said, it is actually also true for subgroups.
Yes.
Yeah. So. Yeah. I'm not sure whether one can really use it to attack Thomson group.
Yeah, thank you.
If you have more questions, I suggest you to discuss with Professor Li during the tea break. And let's thank our speaker again.
Okay.